but I think the big question that a lot of you guys have in mind is, what are we doing for homework? And you'll find soon enough, if you haven't caught on by taking a former class of mine, that what I like you guys to know is the things that we cover in lecture. And I don't just mean like, oh yeah, I've seen that and I recognize it. I mean, I want you to know it, like own it. And I thought the best way to get everybody off on the best foot, if you have a better foot, I guess, is to make the homework the lecture material, so that when we have a quiz, say first one scheduled for next Monday, that the questions will come from lecture examples, things that we did in lecture. So you go in the lecture material, that'll, I think it'll serve two purposes. Number one, make sure that you actually not just pay attention on the day, but go back and make sure you take ownership of all the lecture material. But secondly, the things that I'm covering with you are the things that I think are most important. So it would be weird to assign homework problems that are other stuff that are different than. And of course, if you want practice, like, well, I want to see a different side and see if I can do number crunching types of problems. Well, the book that you found a PDF link to has, I don't know, 80 chapters or 80 problems per chapter or something that you can, I'm sure, as you guys are resourceful, find solutions for, so you can work out the problems. And if you can't figure them out, the answers are somewhere on some cheat site, and if they're not, guaranteed Gemini can do them for you. So you can get all the practice that you want, but the things that I really want you guys to take ownership of are the things that we're doing in here. And it's you'll find that depending on the text, sometimes the books have more emphasis on what's really going on and how's the theory and can I work out these results. And other ones really have I don't know, plug and chug is probably the best word for it, kind of nature, where they expect you to find equation 2316 and plug in numbers. And I just find that to be the most useless thing in the world. Because you could probably train a monkey to do that, to plug numbers, maybe not into an equation, but close, right? So I want you guys to understand that how did we arrive at these equations in the first place? Not an exercise in can you plug numbers into an equation. And of course, there's sort of problems, there's sort of somewhere in between. But anyway, focus on the things that we do in lecture, and I think it would be good. And that'll also be relevant when it comes to exams, that you'll tend to find things that are very similar to, if not directly extracted from lectures. Yeah.
So by lecture material, you mean the entire process from like start to finish?
I do. Okay. I do. And that's the process of thinking and doing science. Think about if you were taking a course on logic. You would. It's the whole process of thinking through what kind of assumptions can I make, and from there, where can I go on to the next step to come to a conclusion. It's not like, oh, here's the answer, memorize it, or put it on an equation sheet. This is like that. And of course, real problem solving in engineering, same story. It's not like you're going to, hey, design this bridge. Well, where can I find the equation for that? Or the answer is like, just sit down and think about what matters and work through all the details. And it's a process. And of course, these things, it's the same story. So it's teaching you, first of all, what kind of fundamental things can I assume to always be true? And coupled with math, then how can I use them to arrive at an answer? Which in the case of the present material is finding electric fields and forces between things. And so we're going to do a bunch of examples along those lines today.
And then will it be exactly, the same stuff? Same numbers?
You have or like say for the first one, absolutely.
Yeah.
I'll make it.
First quiz.
Yeah. So I'll guarantee that. And, when it comes to exams, it might be a variation on something that, but yeah, close enough that if you've studied it and you feel like, yeah, I own this. Not like I've plugged it into my memory, but I can reason my way through and understand what's going on here. I think you'll be very comfortable. Not just on homework quiz, but exam as well. Okay. All right. So let me see. Was there anything else? No. So what happened on Monday, obviously, was we had a remote lecture. I don't know how many of you guys were in like actual on the remote end of things. I know we had, 8 in class? Students, because I came here and I told you I was going to. So we recorded the lecture in class. I think there were 8 of us. I think there were 8 of us. But
there are about 8 online too that watched it.
For the rest, you were. That doesn't go well. So what we had done on Monday was try to imagine a force between. You can see this on the boards or the 2 screens. There was a continuous this big rectangle imagine that's something like, this marker that acquires charge maybe by friction. So you rub some material like a cloth against this and it acquires a surface charge. And so it's some linear shaped object that contains charge that I labeled big Q. And then there's some other charge, sitting here that's nearby. And the question that we were trying to address was, well, how do you find the force between those two things, the long distribution and the individual charge? And of course, it shouldn't, if you've distributed all of that charge, capital Q, over this object, it's definitely not the same answer. Well, I guess it could be the same answer as assuming that all the charge sits in the middle, but we discussed that, and for the 8 of you who were here, what shape is required in order for the force between an extended distribution of charge and some other thing to not depend on, so if I wanted to have charge Q and some object here over which some other charge is distributed, and if I want to say, okay, so here's the geometric center, I'm going to assume all the charge Q sits here and calculate that force. In order for that force to be the same as the actual force that you get when you spread it evenly over the object, what does the shape of the object have to be? Yes, say it louder. Spherical is the only way that it works. And that's true for gravity as well. So if it doesn't work for, this isn't obviously a sphere, if this doesn't work, then what we were up to last time was trying to figure out, well, how bad is the approximation? If I do assume that all the charge sits at, the most reasonable point, and I think everybody would say most reasonable is right in the middle, then, and I calculate that force as compared to the actual situation, how bad is it? And if this is, and obviously if it isn't the correct answer, then my next best thought is, how about if I chop it in 2 pieces and imagine that right here I have Q over 2, and right here in the center of the other piece I also have Q over 2. And, it's the same story. Calculate the force, it's the sum of forces now, the force between these two and the force between these two, add them together and you get a total. And that should be a little bit closer to the real answer because you're, in some sense, distributing the charge. And then, of course, you can make 3 and 4 and 10, whatever. You can chop it into a lot of pieces and assume that, whatever, what is that, 3, 6, that's 10 by chance. 2, 3, 4, 5, 6, 7, 8, 9, 10. So Q over 10 on each of them. And, so I should be getting, and I calculate now 10 forces, right? The one between these two, the one between these two, the one between these two, and add them all together. And I should be getting something pretty close to the continuum answer. Should be getting better and better in a limiting sense. And so what we attempted to do last time was write out what that would look like given, this is n equals 1, the number of pieces, 2, n equals 10 in this case. So in a general sense, an expression for what should the force look like in terms of n. And what we got was that this sum right here. So you have, this is, think about KQQ, when we think about Coulomb's laws, the magnitude is K times, right, it is Q1, which is this guy, times Q2, which is, well, it depends on what n is. We're writing it as Q over n, whatever the other pieces are, and then the distance, and that's the, and distance squared, of course. The distance worked out to be, this was A, the total length of the rod was L, and I don't think I want to take the time to go back over how that denominator worked out, the term, but this A plus L over 2n plus I L over n, and then, sorry, need a sum, I equals 0 to n minus 1 was the way this worked out, and that was a magnitude. If I want to backtrack it, put a direction on it, but we came up with that expression, and I think that was right at the end of the hour. I was like, so how good is that as comparing to what we would think of as obviously an integral, this uniform distribution of charge? And so I had that morning made it on a spreadsheet, but I decided to do it one better. So I made this after class. And what this is, well, n is number of pieces, and I can change it with the slider. There's the little q, the one on the left. Here's the object at the moment. It's putting all of it at the center, so it's this first situation. The length of the object is adjustable, and the separation between them. So if I change A, you can see that that just moves the thing away, and if I change L, I make the rod longer or shorter. And so what I decided to calculate was, well, here's the force that you get from the sum, from calculating that. here's the force that you would get from the integral if you treat it correctly, and here's the error. So you're underestimating by 13% in this case. And, of course, the big problem is that I'm putting all the charge right at the center, and so it ought to get better as I increase the number of pieces. And so cutting it in half, I drop that, from 13 to 4. And of course, that's specific to both the length and the separation distance. But as n grows, you see that percentage dropping to, something very small. And of course, if I drag it far enough, drag faster, we're down at 100 pieces. I'm down at, very tiny error as compared to an integral. So first thought is this. What do you suppose, I mean, you might have already seen if you were paying attention to me sliding slides around, but what do you think leads to the, this 13% error if I didn't do anything with n and I left it as one piece, but I could change a or I could change L? What would I have to do to L, first of all, to make the difference between the sum and the integral get better? Do you think a shorter rod? Yeah, of course, shorter, because if it's short enough, well, it's all stuck at one location anyway, right? So it doesn't look like an extended object as L goes towards 0. And of course, you watch that percentage drop as it gets shorter. So of course, that's the effect. What about A, though? Yeah, and why do you suppose, and it does get smaller as it gets farther. Why is that? What would be the argument in your head for, like, why should I expect a smaller error when I'm, what the error is the charge is really spread out, and I'm assuming it's all sitting right here. And why is it better, when it's far away?
The distance between Q at one end and Q at the other end.
Yeah, it's not a relative distance, right? Relative to A, it's not that much farther to the back end of that rod as compared to the front end percentage-wise. And so, yeah, of course, which is exactly the same thing scale-wise that you're doing when you're decreasing L when it's up close, right? You're saying that, oh, the rod is short as compared to the distance between me and the rod. And so you can accomplish that either way, either by putting the rod really far away or by making the rod really short. And it's the same either way. And of course, if I could drag this to A goes to infinity, it's the same result, meaning, the point charge and the extended rod, if it's far enough away, you can't tell the difference, and you should expect the field to be identical in both cases. But of course, the big thing that helps, regardless of distance and length of the rod, is increasing L, or N, the number of pieces you chop it into. And so why don't we do, since we have, like I said, go back to the lecture to see how the series solution comes about. The big thing is, how do you come up with this and make sure that you get the terms right? But let's do it in terms of calculus today. So we do it as an integral and see how that works out. And it might be good to look at this and sort of make an equation, an integral of this. If you think about this sum of terms, especially when n gets large, the whole, I don't know how you were introduced to calculus and integration, but that notion of an infinitesimal, the things over which you're integrating becoming infinitesimally small, and you're adding up an infinite number of them. So the best way to think about that is that n is going to infinity in this case. So n is getting really, really big, which obviously has a consequence on this guy. The charge pieces on each of these is getting really, really small, and that becomes that infinitesimal, the one that, in our case, so if I'm thinking about, okay, k is just a constant, q is just a constant, the one on the outside. This thing is going to become a dq. So this becomes the infinitesimal piece of charge that's going to play into the integration part. And if you think about the denominator, I'm going to have something to do with distance squared. And of course, a is a constant, so that's got to be fixed. And if you think about these two terms, in the event that n goes large, what's going to happen to the first, the L over 2n, obviously? Yeah, that one disappears. What happens to this one as n goes large? Answer's probably it depends, right? Well, this guy is the one over which, this is the one that's starting out as a 0, but it's ending about as big as n ends, right? So this becomes the variable, right? At the low end, that's a 0. So this thing plays the role of 0, right? But at the high end, what's it turn into? Very nearly. Yeah, well, 1 times what? Times L, right? So this is a variable that, starts at 0, ends at L. So it seems to me that ought to be written like this. And I'm thinking about, of course, you're looking at this like, how is this going to work out? This is my variable and I'm integrating. We'll fix that in a minute. Don't worry about this. But really, if you think about what we're integrating over, this is going to be written in terms of an x in just a moment. And the x variable is the one that we want to go from 0 to L. And if I do this and make an integral of it, I should get the force. But I need to figure out how in the world this variable goes along with having a dq instead of a dx, obviously. But they're certainly related, right? Because if I think about, wait, this doesn't look so hot, does it? This, if I think about this rod, it just turned purple, and I think about one little, imagine that's infinitesimal. I couldn't draw it if it was actually, but it's got a length to it, right? There's a length dx, and on that there's some charge dq, and those things are certainly related. How long, if we assume total length, as we've been doing, is L, and that the total charge is Q, how do you suppose we can relate the length of the piece to the charge that that piece would contain if it's uniformly distributed? I mean, they're definitely proportional, right? If you had twice as long a segment of a rod, you're going to have twice as much charge on it, 3 times as much as, 3 times as long, you get 3 times as much charge, right? Does that make sense to you guys? So we know for sure that they're proportional. So dq is proportional to, dx. And the only thing that we need to turn that into an equation is a proportionality constant, right? So this is a proportionality. If I wanted to say equals, I need to invent something, or I've been invented before, so I don't need to invent it. Lambda is that proportionality constant, and what would the units of lambda be? Because that will tell us something about what it represents. If you think about solving for lambda and you think about what is the unit of q and what is the unit of x, what do you get? Anybody have a good idea? Yeah, it's coulombs per meter. So what would that, so how much charge per unit length? You guys see that? Coulombs on the left is the charge you divide across. So coulombs per meter, they call it linear charge density. So linear because usually density we think of as a per unit volume basis, but this isn't volume, obviously, it's per unit length. But linear charge density is what we need to relate those. And of course, when we do that, and by the way, this charge density doesn't have to be a constant. You could imagine a situation where, if I was charging this with a cloth, maybe just the way that I'm rubbing it or something, there's more charge, at the far end than on the close end. That could be a function, meaning that lambda could be lambda of x, something like this. And if that's the case, the definition doesn't change in the sense that if you thought about how should I define lambda, well, divide the dx across, and you'd write that regardless as this. And so that is the definition of lambda every time. But many times in problems that we do, we're going to assume that it's a constant in the sense that you can just plug in a value and pull it out of the integrals and don't have to. But if it was, excuse me, if it was a function, then you just have to be given the function, whatever it is, and it becomes part of the integral. And why does it become part of the integral? Because when I put dq as lambda dx here, you can see that this thing would become, integral for the x variable, k, q, lambda. I'll write it generically so that we can see that it could be a function. But that would be lambda of x dx plus over a plus x squared, right? So the possibility exists, sorry about my x, possibility exists that this guy could be a function, it could be anything. But of course, if you make it too ugly, you might run into a situation where I don't know how to integrate that. I'm trying to think if there are cases where most of the time when we're dealing with problems, I don't think there's a good argument for saying that there's a general situation like in nature where that tends to always take on some form where it grows along the length or anything. I think for the most part it's fair to assume that there's no particular form that this ought to take on in any given case. In volumetric distributions, that's maybe a little bit different when we get to Gauss's law. We're going to have something similar but distributed over a volume. It's going to be a volumetric charge density. But for now, what we're going to do is assume this guy's constant, pull it out of the integral along with the k and the q, and do the math. Of course, what are you going to get when you do that? A q lambda assumed constant integral 0 to L of a plus x squared. So how are you going to do that? Actually, why don't you do that? And let me know what you find, just to get a little bit of practice. Get this. And of course, we plug in negative k q lambda 1 over a. Sorry about that. Is that? Can you guys see that? A plus L minus 1 over a. So looks like it's equation. So that result, if you, by the way, is this thing in parentheses positive or negative? Because L is going from 0 to something positive valued, right? So in every case, length, this thing is, this is the length. It's not a negative variable, right? So this first fraction with a bigger denominator is a smaller number, right? So smaller minus the bigger becomes negative, which really means we can flip the terms and flip that sign if you wanted to. But, and why is that useful? I mean, plug in numbers and recognize that, but just to realize that it's not somehow giving us a negative answer as compared to there's no negative coming out of this guy. And so if you're looking at this, you're like, wait, why is that negative? It just kind of looks like it at the moment. It's not really a negative value. So if you compare that, that's the value, that's what I plugged in for these calculations, for this second line for the integral result for given a value of L and A, this is the integral. And of course, the n doesn't affect the integral because it's assumed to go to infinity, right? So this is just a result of the integral, this is a result of the sum, and that's how those two compare. And do you have any questions on that? How to make sense of it? And if you want, I'll save this GeoGebra if you want to mess around with it and click on the boxes and see the inputs and things if you want. Send that to the class so you can mess around with it. All right, questions before I move on to another example? Yes?
Could you explain again real quick, just going from the dq to the lambda and just that relationship with a constant?
Yeah, so you mean how this turned into lambda dx?
Yeah.
It really is, I mean, if you think about this picture, you have charge distributed on a long object like a stick or something. And what we should for sure recognize from the outside is if I just like chop off a piece of the stick and I'm holding it there, and so long as the charge had been distributed uniformly along it, I know for certain that the longer the piece that I take, the more charge is going to be sitting on it, right? And not just that it grows, but it should grow proportionally. So twice as long a piece should have twice as much charge sitting on it, and 3 times as long, 3 times as much. And so that proportionality was a sure thing. So that's why I first wrote this as, this tilde, which is meant to read proportional to. Sometimes you see alphas to indicate proportionality, but you know that these guys are related and proportional, but to say that they're proportional just means that I can make it an equation so long as I come up with the name of some proportionality constant. That was, that's really the spirit of what's going on. I recognize that as all these DQs are sitting at different locations, and as I'm really sweeping across this thing, really to add all of their contributions to what was previously a sum and is now an integral, I know that that has to do with sweeping across distance, and so they're related. I needed that to be an integral in terms of x, not in terms of q. Obviously, because this, like, where are all the pieces dependent on x? And so we just have to define that proportionality constant and use it. So that's really what's going on there.
And the little q and the k are both constants.
This is the other guy. This is that one that's experiencing the force, and that's not changing. What we're saying is this one's feeling a force due to all the tiny elements that we think of as making up this entire thing, and each of them is exerting force on this guy. But this guy's charge is just sitting in the equation as a constant. And in fact, where we're going to go next is just to say, well, what if there was nothing here? What if there was no charge? And instead I just indicated a point in space and did this. Would there be anything meaningful to talk about at this location? And what if I pose that as a question? Would there be? Would this problem make any sense or be meaningful if I got rid of that and said, and maybe obviously give this a different name, but what would I have sitting at point P that would be meaningful to still calculate in this context? Any ideas? Sorry. There's no force to experience it? Yeah.
Would you calculate the charge at point P?
Well, so we had a charge at point P, and I just deleted it from existence. So the question is, due to all, yeah, I mean, if there's, can a force exist if there's nothing to feel it? Well, no, but something can, because where'd that force come from? Why would a charge have experienced a force in the first place?
Charge itself.
Because what?
Because it's charged itself.
You mean like the self force? We go to.
Well, it has to be charged. Something else charged it.
Well, so when you get into the self part of electrodynamics, we've gone to great lengths to try to avoid those sorts of issues. We will discuss what we thought was the answer to energy required to assemble fundamental particles, but it turned out to be wrong. But yeah, what do you have in mind?
The strength of the field at that location?
Yeah, why are you saying that? What equation are you thinking of that relates to two? So that F that we were calculating, what does it depend on? If you guys read the definition of the field, right? What's the, how do I relate this to here's the charge that was experiencing something, and what that something was this guy, right? The electric field. So if I don't have a charge to experience a force, well, there was still the field in that space. And the question is that, should I care? And it turns out we care way more about fields in this subject than we do about actual things experiencing the forces from those fields. It's kind of weird because we didn't do that in 231. We didn't say, we're studying orbital motion. It wasn't, we find the force on the moon, keep it in orbit, and find the trajectory, and never stopped and said, hey, suppose there is no moon, but I'm sitting out here in this location in space, it's far from Earth, and how strong is gravity there? And what does the gravitational field look like? And it wasn't really a big concern. It becomes much more of a concern now. And part of the reason for that is that the fields aren't just these abstract things that, you can think about. I think if you think about them incorrectly, you can think about them as these mathematical tools. Like the real thing is this and that, and this guy's just a mathematical tool. But the idea is that we know now that the fields are just as real as the things that experience the fields. And in fact, light is only fields. There's no materials tied to light. It's only electric fields and magnetic fields. And they sustain one another, as it turns out, mathematically in a way that we can prove at the end of the course. So those fields are meaningful. They carry energy, they carry momentum, potentially angular momentum. And so it is a meaningful question to ask. Like, what is the electric field out here, even if there's no charge to experience it. And of course, the transition to next chapter is all about fields, and so I was thinking that our examples now are going to be like this, except let's leave this out. And instead of being E, or instead of being F, it's going to be E that we're finding. Context, the electric field, which of course, if you take the, just think about it like this, divide out the charge, so they get rid of it from the force expression, like that, and I don't need it, and I get the effect is that I get this, what was F divided out the Q becomes E, right? So that's, let me take a picture of this, and then we will move on to some other examples. I want you guys to have no excuse to know lecture material well. And all right, so we have a bunch of examples. I think I'm not going to start the really hard math one. Let's start with the work area. And so we're going to, the questions, the question every time is going to be, given some distribution of charge, what's the field at some point in space? And what you'll find is that if you're at all creative, you're going to go beyond the capabilities of math that can be done by hand. So you have to stick with simple geometries. And first case that's pretty easy is circular arc segment. So imagine there's a center, and so center meaning that if I continued the circle, that would be the center of the circle. But the charge distribution is confined to this section of the drawing. And so we have some total charge on there distributed. I'm just going to make it symmetrical on here. You can think of it as the horizontal axis. So that the total angle, call it phi, but it sweeps out. I'll draw that. Okay. So the total angle is phi. Total charge is Q. The radius R. And here, the center, but I'm going to call it point P, because we're going to use P as a general, think about P for a point in space where each example we're going to ask to find what is the field at that location. So, find E at point P. And of course, if you want, just to help with the abstraction, if you knew this answer and you multiplied it by, you decide to stick a charge here, what you're really finding is, in that context, what would you get then? If I stick a charge there to experience the field, what am I really finding then? Force. So if you want to, I don't know if your brain just doesn't like thinking about abstract fields yet, well then, help it out by like, but if I put a Q here, which literally means whatever result we get, multiply it by Q, and you'd be finding the force that some charge would feel if it was sitting at point P. But we're going to leave that out and do this abstract level. So the expression that I had up there for finding the force as an integral, if you think about that K, there was a dq over r squared, and then if I want it to be a vector, I'm going to need some direction. So there's going to be some unit vector, which I'm going to label r hat to give us a direction. This is our generic form that I'm going to follow every single time. I just have to sort of massage it into a way that I can actually integrate it and make sense for a problem. So think about this as this part is the, I'm sorry, E. If I had another Q in there, if I stuck a Q in here, that would be a force. So this I should think of as a DE, and what does that mean? Well, look at the fact that I have an infinitesimal charge. So I'm going to arbitrarily say, let's think about this little piece of this arc. And on that, there's charge dq. Probably should use, let me change this to a lowercase, just because it's more common to do that. So there's total charge, little q, is what's sitting on this arc. On this short segment here, there's infinitesimal amount of it, but it's it's represented by this guy in the equation. Obviously, there's this R is talking about the distance between where that charge is and the place where we want to find the field. So, you know, this is the R in the expression, and of course it's squared. The R hat, every time, definition of this guy, think about from this location where the charge is sitting, pointing in the direction to P, that's what R hat represents. And what that ultimately suggests to us, I mean, think about if this was the only piece of charge. So, you know, if that was, you know, get rid of the rest of the arc, all I have is a charge sitting right here. What it's telling me is that the field always points radially outward, away from itself. You know, because if I want to know the field here, R vector is going to point there. If I want to find the field here, it would be pointing this way. If I want to find the field here, it's pointing that way. And so what that really is just suggesting to us is that any charge, if I had it, and it's assumed positive in this case, creates a field that radiates out from itself. Does that make sense? And so that's the meaning of this guy. It radiates away from the dq. And of course, if dq ends up being negatively charged, well, that's going to be taken care of because this thing's going to look something, there's going to be a lambda in there, and it might be a negative amount of charge per unit length. And that's going to then turn all these vectors inward and suggest that for negative charges, that the field lines do the opposite, they point inward. Does that make sense? So that directionality is not going to change this guy, it's just going to be in this dq, there's going to be something about charge density, and in there, that sign would flip. Okay, so in this particular case, when you're thinking about dq, in the same way that we had before, this lambda dx is what we used before to write dq, as in charge per unit length times the length gives me the charge. This is kind of awkward, right? We don't want like a circular arc segment. So dx doesn't look like the right length to be using. What do you suppose is the right length to be using? You know, how would you indicate this length for an arc segment? What would be an easy thing to do? Yeah, or I think I made it a phi, right? So what times? So you couldn't just write it as a d phi, right? There's a something d phi, because d phi doesn't have units of length. R d phi would. So, and I'm going to use, you know, so this is the generic R that I drew here, but we've defined the actual radius as capital R, so I'm going to write this as the actual radius, so times d phi. So this is, you know, this is an arc length. And you guys all, you know, so often S is what we call arc length at some point in your education, I think. And do you remember that there's the relationship between these three variables that has to go like that? What's the unit of phi have to be in this equation? In order for that, yeah, so if you want to remind yourself, maybe put a little radian on there, because if that was degrees, it would be crazy talk, right? What is the most familiar version of this equation that you've probably had the result memorized from already back in middle school? Like for a particular value of phi. What did you learn about circles in middle school? Circumference, and it's what? Yeah, 2 pi r is the circumference, and all that's saying is it's exactly this with a full sweep all the way around. So turn this into a 2 pi, and you get r times 2 pi, and that's the arc length, but it's the arc length all the way around, and so we tend to call that circumference, and you know, you've known that for ages, right? Well, of course, it's true for a half circle. You put a pi instead of a 2 pi, or for a quarter circle, or for anything else. So any radian sweep of that angle gives you an arc length. And of course, we're doing the exact same thing right now, except we want it to be an infinitesimal length. And so the only idea is that we're going to make this infinitesimally short, which means an infinitesimally small sweep of the angle, and add them up as you go around and figure out what happens. Okay. All right, so this, I guess I'll write it over here. So far that gets us to here. We have integral k. dq is going to be lambda times this version of a length, so r d phi, over the generic r is the same thing as the actual radius, so that's r squared. And then I have this guy, which at first looks maybe inconsequential, but it's not. And this is everything about direction. And what's important about that to recognize is that, you know, if I take it maybe and put it over here, point that r hat this way, what we're really finding is that this is the direction of the field due to this little charge. But then, you know, suppose that dq is sitting up here. This guy's contribution points this way. This guy's contribution points this way. And that one points this way. And so what's happening is this guy's changing all the time. If you start adding, and you're like, okay, let's first start with the field due to this piece, and you start making your way across and make, you know, this thing is sweeping, you know, as it goes. And so we need to obviously factor in this directional change. And maybe the easiest way to do that is to recognize that depending on how we want to do this, and maybe we can just do it like this. Let's think about this being the theta equals 0 direction. Maybe we can sweep positively this way, so positive theta that way. So this is a unit vector, and there's some angle. And of course, if you think about the actual thing, this angle and that angle, as high as it gets is given by, or below this gets to indicate where the actual physical object is, and on the other end it's the same story, right? So that angle and this angle match. But the r hat, we have to have an expression, and I'm going to write it in terms of this theta, just like you would in a unit circle. And what does that look like then? If I wanted x and y components, or like this, what would it be in terms of theta? R cosine theta, except what's r? So let me write it this way. The magnitude of the vector times cosine of theta, and that's the I hat. What is this? It's just 1, right? So, okay, so that literally just means the x component is cosine theta, and what's the y component? Sine theta. So, and then again, magnitude 1. So we have this guy, and so now we have to plug that in there. And what that obviously suggests to us is that we have two integrals to do, or one integral over a vector, depending on how you want to look at it. So we have k, lambda, r d phi, r squared, and of course I could have in the last step canceled one of those. And all of these guys, by the way, if I wanted to, I could pull them out as constants, right? But this is what we have. So what's being integrated? Well, for the x component, I integrate cosine of theta, I turned thetas into phi's somewhere. Apologies for that. My Greek is being transformed. They're all phi's, phi and phi. So my integrals are, for the x component, cosine of phi d phi, for the y component, sine of phi d phi. And then, of course, range of angles for phi. So if you think about that range, if I gave you, I shouldn't use the same phi. Maybe I call it phi prime in total. So whatever if you made it a number, like if this whole sweep was symmetric about the x-axis and was 90 degrees, then it's going from negative 45 to positive 45. So, but so obviously you know how to integrate a cosine. Just think about, you want to actually do the case where let's make it a pure right angle. So I'll make it look like a right angle like this. So here's the angle. That's a right angle, and in that case we would be integrating from negative pi over 4 to pi over 4. And so right. Yikes. Okay, yes.
Integrating from negative power to power 4, why not the other way?
You could. And what you'll, on the cosine term, of course, it won't matter because it's going to look like, there any consequence, the sine is going to, I mean, for this particular case, it's going to cancel. In what sense will it? So if you get a,
It would make sense.
I guess in principle, as I'm iterating my d phi, I should be thinking of going from the negative value to the positive value, right, as it grows. Because you can't, with the with the symmetric function, once you integrate sine, it becomes symmetric about 0. So as you'd expect, there's no consequence. It's going to cancel itself either way. But the x term, let's do it. So the x term, this leads to a lambda over r times sine of phi I hat minus cosine phi, oops, j hat, evaluated from, let's say, negative pi over 4, Very, my hand just made it looks like a Chinese character. Pretty cool. So if you do this, work it out and tell me what the two answers get if you flip the signs, and we'll discuss what that means. And just we'll leave these constants, but the important thing is what do I get here? So sine of pi over 4 minus sine of negative pi over 4. What do you get? Over root 2, so 2 over root 2 in that case. Is that right? Yeah. Yes.
Because we are worrying about the directions, would we need to integrate it from 3 pi over 4 to instead lines 0 to it would be that way?
Say it again.
Because we defines.
Well, it's the r hat vector's direction that we don't care about. So this guy is, if you started with let's consider the contribution from this guy. Here's the original location of r hat, and then as I go across, it's doing that. Right. Okay. So relative to these axes, I should be thinking. The only thing that's vector in the equation is that, and it's r hat's angle that really matters to us. So does that? What did I say it was? 2 over root 2. So 2 over root 2, right, for the first term in the I hat. Minus 0, because cosine of pi over 4 and cosine of negative pi over 4 are the same thing. So this is, I'll just say plus 0 j hat. And obviously, I think the issue that we run into is we do need to go from negative to positive, as we sweep across, because the idea of that d phi is it's an increment that you're automatically expecting that it's adding to the previous value, not subtracting from. In this sense, it's like when we were back in this summation version, we were expecting that we're adding to the what would have been related to the value n in the series. But anyway, obviously it depends on what those limits are. Question: what do you suppose happens if this arc segment becomes a full ring? Like, what happens to the field? What happens as a result of the integral when we're plugging like 0 to 2 pi?
Kids.
Yeah, and why? Yeah, so obviously the math says, oh, there's no field. Why should that be the case? Yeah, I mean, if you think about those, he's drawn the picture over here where all these are pointing in different directions. Well, if we went full circle, then some of them are pointing to the right, and some are pointing upward, and some are pointing leftward, and some are pointing downward. You add all those together as vectors. All the rights cancel the lefts, you have to cancel the downs, the diagonal that way, cancel the diagonal that way, and you get nothing. Which is, it's weird. You said you'd be sitting at the center of this charged object, or you could place a charge at the center of it, and it feels nothing. But that's not terribly surprising. And in fact, the way that it works out with electrostatics and with gravity is that while that's sort of a 2D, very, so if you had a ring of charge like this, while the field is zero right here in the center, it isn't zero off center, like right here or any place else. But what's interesting, and we'll see this from Gauss's law next time, is that if instead of being a ring, this thing was a spherical object, then everywhere inside of it, the field is zero, not just at the center. And so it'd be imagine something like this. We find out that geologists have been wrong all along. Earth only has a crust. There's no magma, there's no core, it's aliens made it. Earth is an artificial, very natural looking artificial object. But we drill a hole, the Russians decide they're going to get some oil out of some deep reserve or use geothermal energy. They're like, oh my gosh, it's a void in there, what the heck? And they jump in there, and you got this spherical shell of an Earth that's kind of like a giant ping pong ball, and you jump inside, and immediately, not just at the center, but everywhere inside, you'd be as weightless as you would be in space. And it's a cancellation that occurs much like this does at the center, except the uniqueness of a sphere is that it doesn't just cancel at the center, it cancels everywhere within that object. So, and Gauss's law speaks directly to that when you read the next chapter. Got way less done than I wanted to. We're out of time, but we'll finish up these examples on Friday. Yes. Yeah. Yep. It's pointing away from the charge.